Imagine a whole world made of diamond, not just a few carats, but an entire planet sparkling under the light of its parent star. This isn't a fantasy from a science fiction movie, it's a real possibility out there in the vastness of space. Scientists are seriously considering that such worlds exist. One of the most famous candidates is a planet called 55 Cancri e. It's captured our imagination for a very good reason. It makes us wonder what other incredible things are waiting to be found. The universe is full of surprises, far stranger and more wonderful than we can often comprehend. This idea of a diamond planet challenges everything we thought we knew. We are used to planets made of rock or gas or ice. Those are familiar. But a planet composed largely of pure crystallized carbon, that's a whole new category of world. The universe, it seems, has a diverse planetary cookbook. It uses different ingredients and different cooking conditions. The result is an amazing variety of celestial bodies, and 55 Cancri e hints at just how exotic these recipes can get. It opens our minds to the sheer creative power of cosmic chemistry and physics. The significance of finding such a planet goes beyond just its sparkly nature. It tells us that the building blocks for planets can be very different from what we see in our own solar system. Our Earth is rich in silicon and oxygen, but what if a solar system forms from a cloud that is unusually rich in carbon? The planets that form there would naturally be very different. They might be carbon-rich worlds like 55 Cancri e is thought to be. This changes our understanding of how planets form everywhere. It broadens our cosmic perspective in profound ways indeed. Thinking about a diamond planet is, quite simply, awe-inspiring. It reminds us that we're just beginning to explore the cosmos. There are countless stars out there. Many of them have planets, and some of those planets could be incredibly strange and beautiful. The universe is a laboratory of unimaginable scale. It is constantly conducting experiments with matter and energy. We are the lucky observers, piecing together the story of its creations. Each new discovery, like the possibility of 55 Cancri A, adds another fascinating chapter to that grand cosmic narrative. So how do you find a potential diamond planet millions of light years away? You can't just point a telescope and see it sparkle. Not yet, anyway. The discovery of 55 Cancri A was a triumph of clever astronomical techniques. Scientists first detected this intriguing world using the wobble method, also known as radial velocity. They observed its parent star, 55 Cancri A. They noticed tiny tugs, a slight back-and-forth movement of the star. This wobble indicated that an unseen planet was orbiting it, its gravity pulling on the star. It was a subtle dance revealed by light, but the wobble method only tells you a planet's mass and its orbital period. It doesn't tell you its size. For that, astronomers needed another trick, the transit method. This happens when a planet passes directly in front of its star from our point of view. When 55 Cancri e made this transit, it caused a tiny temporary dip in the star's brightness. Think of it like a tiny gnat flying in front of a distant lighthouse beam. By measuring how much the light dimmed and for how long, scientists could calculate the planet's physical size, its diameter. Once astronomers had both the mass from the wobble and the size from the transit, they could calculate something crucial, the planet's density. And this is where things got really interesting for 55 Cancri e. Its density turned out to be very high, much higher than Earth's. This high density was a major clue. It suggested the planet was made of something much heavier than ordinary rock. Scientists began to consider what elements could account for such a dense world orbiting so close to its star. The pieces of the puzzle were starting to come together. The initial discovery of the planet itself happened back in 2004, but it was later observations, particularly with the Spitzer Space Telescope, that refined its characteristics. These observations helped pin down its size and temperature. Scientists were able to build a more detailed picture of this super-Earth. A super-Earth is a planet more massive than Earth, but lighter than giants like Neptune. And this particular super-Earth, 55 Cancri e, was shaping up to be a very unusual one indeed, with its high density pointing towards an exotic composition. Why diamonds? Why would scientists look at a dense, hot planet and think diamond? The answer lies in the chemistry of its star system. The host star, 55 Cancri A, was found to be unusually rich in carbon compared to our Sun. Stars and their planets form from the same swirling cloud of gas and dust. So, if the star is carbon-rich, it's logical to assume its planets might be too. This is a key piece of the puzzle. Imagine a planetary system where carbon is more abundant than oxygen. The planets forming there would be very different from Earth. With this carbon-rich environment, scientists started to model what 55 Cancri e might be like. The planet orbits incredibly close to its star, much closer than Mercury orbits our Sun. This means it's scorching hot, with surface temperatures potentially reaching thousands of degrees Celsius. Combine that intense heat with the immense pressure deep inside a super-Earth. What happens to carbon under such extreme conditions? It can crystallize, it can form graphite, and under even greater pressures, it can form diamond. This is the core of the diamond planet hypothesis. So the theory goes like this. 55 Cancri e could have a thick layer, perhaps even a substantial part of its interior, made of diamond. This wouldn't be like the diamonds we find on Earth, which form deep underground and were brought up by volcanic eruptions. This would be planetary-scale diamond, a vast solid ocean of crystallized carbon. Other layers might include graphite, perhaps some silicates and a metallic core, but the sheer abundance of carbon, combined with the planet's mass and temperature, makes a diamond-rich composition plausible. It's a fascinating outcome of planetary science. It's important to remember this is still a leading theory. Observing exoplanets in such detail is incredibly challenging. Scientists use models and indirect evidence to piece together their nature. Later research has suggested that 55 Cancri e might have a thick atmosphere, and the exact nature of its carbon content is still debated. Perhaps it's not a solid diamond surface, but a world with carbon in other exotic forms. But the initial data pointing to a carbon-rich, super-dense world ignited the exciting possibility of a true diamond planet, forever changing how we view planetary diversity. The discovery of planets like 55 Cancri e, whether they are pure diamond or something else entirely exotic, has profound implications. Scientifically, it shatters any notion that our solar system is the standard model for how planets form and what they are made of. The universe is far more creative than that. It tells us that planetary formation is a flexible process. It depends heavily on the chemical ingredients available in the primordial disk around a young star. If you change the ingredients, you change the planets. This opens up a whole new field of comparative planetology. These discoveries push our technology and our theories to their limits. To understand these distant worlds, we need more powerful telescopes. We need more sophisticated models of planetary interiors and atmospheres. Each new strange planet challenges our assumptions. It forces us to refine our understanding of physics and chemistry under extreme conditions. Conditions of temperature and pressure that we can barely imagine, let alone replicate easily in a lab on Earth. These cosmic laboratories are teaching us fundamental truths about matter itself. They are cosmic puzzles waiting to be solved. Beyond the purely scientific, imagine the societal implications, even if they are far off. If diamond planets or planets rich in other valuable resources are common, what does that mean for the future of humanity? Could we one day mine other worlds? It sounds like science fiction now, but so did flying to the moon a century ago. These discoveries fuel our dreams of exploration and expansion. They remind us that there are vast resources and wonders out there. They spark the imagination of future generations of scientists, engineers, and explorers. Ultimately, the quest to understand planets like 55 Cancri e is about understanding our place in the universe. It's about the sheer, unadulterated wonder of cosmic diversity. Each new world we find, each strange new composition we uncover, adds to the richness of the known universe. It tells us that reality is often stranger and more magnificent than fiction. The universe is under no obligation to make sense to us or to conform to our expectations. And that is precisely what makes its exploration so endlessly fascinating and rewarding. The stars are calling, and we are just beginning to listen to their stories.